Hello students, in a last video lecture we have learned how to construct the circle diagram. Now in this video lecture we are going to learn the actual example to draw the circle diagram and to find out the various parameters. Now let us consider the 14.9 kilowatt 3-phase 400 volt 4 pole star connected induction motor which is tested for no load test 400 volt 1250 watt 9 ampere, and for the short circuit test the 150 volt 4 kilowatt 38 ampere. Draw the circle diagram. Assume the rotor copper loss equal to stator copper loss. Calculate full load current, power factor, slip, rotor CV loss, stator CV loss, starting torque, full load torque, maximum torque, speed at maximum torque, etc. Now from the no load test, we can find out the cos phi 0, and from this phi 0 and the I0 equal to 9 ampere. Now from the short circuit test, we can obtain the phi SC which is equal to 66.1 degree, and ISN, the short circuit current with normal voltage applied, equal to 101.33, and WSN, that is equal to short circuit power with normal voltage applied, and that comes to be 28,444 watt. Now using this data, let us draw the OX as a x-axis and OY as a y-axis. On the voltage vector represent the y-axis. Now from the draw the O dash equal to I0 equal to 9 ampere, that is equal to 1.8 centimeter, with the scale 1 centimeter equal to 5 ampere. Students, always select the scale in a such a way that the diameter of the circle diagram will be around 25 centimeter. This is because it can be all the parameters can be easily visualized, and the measurement taken will be reasonably accurate. Then the OA equal to ISN, and that is equal to 20.26 as per the scale. Now draw this OA by making an angle phi SC with the voltage vector phi. Then join O dash A. This O dash A represent the rotor current I2 dash referred to the stator side, and it is also known as output line. Then they draw the line O dash D parallel to the x-axis. Now the points O dash and A lies on the circle diagram. Now obtain the center by drawing the line perpendicular to the output line, which is a right angle bisector. Now from center C and radius CO dash, draw the circle diagram. Now the point O dash, then A and D lies on the circle diagram. Now from the point A, draw the vertical line perpendicular to the x-axis. Now this AG represents the short circuit power with normal voltage applied. Now here out of that, GF is the fixed losses and AF is the total copper losses, that is rotor copper losses and stator copper losses. Then the line UDAC represent the torque line which bisects or which separate the rotor copper losses and stator copper losses. When you extend the torque line so that it cuts to the circle diagram at point H, represent the slip at infinity. Then measure the AG, that is equal to 8.1 centimeter, and from this we can obtain the power scale, that is equal to 28,440.44 divided by 8.1, that is equal to 3,511 watt. Now the full load motor output equal to 14,900, and therefore the power scale will be 4.25 centimeter. Then draw the line AS 4.25 centimeter. Extend this point A as a AS, and that measure the 4.25 centimeter. Then from draw the line PS parallel to the output line. Then at the point P, intersect the circle diagram. From the point P, join the O. That means OP represents the full load current lagging the voltage by an angle phi. Now when you measure the from this point P, draw the vertical line that is perpendicular to the x-axis, that is PK. then make the marking points M, N, J, etc. Now let us find out the full load current, that is OP, and that is measured 6 centimeter, and therefore OP equal to 30 ampere. Now this is 6 centimeter, and as per the scale, 1 centimeter equal to 5 ampere, it is equal to 30 ampere. Now the power factor, if you measure this phi, it is found 30 degree, and therefore cos phi equal to 0.866 lagging, or otherwise power factor equal to Pk upon OP, and Pk upon OP equal to Pk upon OP, that is measure 5.2 divided by 6 and equal to 0.865 lagging. Now let us see the slip. Slip equal to rotor copper loss upon rotor input. Rotor copper loss, here Mn represents the rotor copper loss, which is proportional to the starting torque, and Pn measure the rotor input, which is proportional to the full load torque. Now here Mn divided by slip equal to Mn divided by Pn, and that measures to be uh, 0.3 and divided by 4.5, and that is equal to 0.067. Thus the slip is 6.7%. Now let us observe here the AE represent the rotor copper loss, and EF represent the stator copper loss, because and these two losses are equal, it is given to us. Therefore this AE is nothing but rotor copper loss, and that is directly proportional to the starting torque. Therefore starting torque TST equal to AE to the scale multiplied by power scale divided by 2 pi ns, divided by 2 pi ns. See, this starting torque equal to AE equal to AE in centimeter multiplied by this divided by 2 pi ns. This is the starting torque, or this can also be obtained by, see here, the starting torque is represented by Mn, and therefore as the voltage vector is vertical, all the vertical measurements are the active power, and therefore Mn equal to starting torque equal to root 3 VL Mn in centimeter multiplied by power scale divided by 2 pi ns. So in this way we can obtain the starting torque root 3 VL into Mn in centimeter multiplied by power scale divided by 2 pi ns in centimeter. Similarly, we can obtain the full load torque, that is equal to Pn equal to root 3 VL into Pn in centimeter multiplied by power scale divided by 2 pi ns, that is Newton meter. Now here, see, the Pn represents the rotary input, and that is proportional to the full load torque. Now the maximum torque is the obtained from the line CQ, which is drawn perpendicular to the torque line, and the Q is projected on the torque line. Therefore, QR represent the maximum torque. And similarly, the line uh, CU is drawn perpendicular to the output line, and CV drawn vertically, which cuts to the output line, measure the maximum output. Now here from the maximum torque, the slip at maximum torque equal to the rotor copper loss divided by rotor input, and therefore equal to Ry divided by Rq. In this way we have obtained the slip at maximum torque. Now let us see the overload capacity. Overload capacity of the motor is given by maximum output divided by full load output. Maximum output is UV divided by PM. That is your overload capacity. Then we can also obtain the, now here the at the point O, it is a no load condition where the speed is nearly synchronous speed, and therefore slip is nearly at 0. Then at point P, this represents the full load point, and therefore slip at the point P is SF. Now at point Q, that represents the maximum torque, and therefore slip is here Sm. And at point A, that is at the starting when block rotor, therefore S equal to 1, and at point H S equal to infinity. This is because the rotary input equal to rotor copper loss upon the slip. And now rotary input here, the at point H rotary input is 0, and this is possible only when rotor copper loss divided by slip, and the slip is infinity, then and then it is possible. Now in this way we have obtained the various labs. Now the question